Welcome to our exploration of electromagnetism. This incredible force of nature plays a crucial role in our daily lives, from the light we see to the electricity that powers our homes, our devices, and even entire cities.
First of all, we have to define what is electromagnetism. Well, the electromagnetism is the interaction between electric and magnetic fields, two invisible forces that shape the universe as we know it. From tiny atoms to massive galaxies, electromagnetism is everywhere, influencing everything around us.
You may not always notice it, but electromagnetism is essential to how the world functions. It governs how charged particles behave, allows energy to travel through space, and even plays a role in the structure of matter itself.
In this video, we will break down the fundamental principles of electromagnetism. We will explore how electric charges generate magnetism fields, how those fields interact with each other, and why these forces are so important in science and technology.
Understanding electromagnetism helps us to make sense of some of the most fascinating phenomena in nature, like how light travels, how atoms stay together, and even how energy moves across the universe.
So, whether you are new in the topic or just looking to deepen knowledge, this video will guide you through the incredible world of electromagnetism.
So, get ready to explore one of the most powerful forces in the whole universe.
And now you must be saying how this little screw with a copper wire around it can't attract metal. It doesn't have a difficult structure. Well, actually it is. An electromagnet works by combining electric current with a ferromagnetic material, such as a screw. And now, when you connect a copper wire to a battery, the electrons begin to move through the wire. This flow of electrons is what we call electric current, such as light. According to Ampere's law, an electric current generates a magnetic field around it. When you coil the wire into a spiral around the screw, each loop of the wire generates a small magnetic field. The sum of all the small fields creates a stronger magnetic field at the center of the coil, exactly where the screw is located. The screw is made of iron or an other ferromagnetic material, concentrates and amplifies the magnetic field because its internal structure allows the magnetic domains, small regions within the material that act like tiny magnets, to align with the field generated by the current. Thus, the screw becomes a temporary magnet. Isn't that crazy?
Why does it work? First, for the electricity, the current in the cable produce a magnetic field around each turn of the coil. Then the coil, when you make many turns, the individual fields are added, creating more intense fields. Then the magnetization, the iron screw amplifies the effect by aligning its own magnetic domains with the coil field. And if you disconnect the battery, the electrons are going to stop moving. The field disappears and the screw loses its magnetism. An interesting fact is that this principle is the basis of industrial electromagnets used in cranes to move heavy metals, in electronic motors, magnetic trains, and even in doorbells.
And now, what's Ampere's law? Ampere's law describes how electric currents create magnetic fields. It is one of Maxwell's equations, forming the foundation of electromagnetism. Like the one we're gonna create. The law is especially useful for calculating magnetism field. In cases with high symmetry, such as a long straight current carrying wire, it's producing a circular magnetic field, a solenoid producing a nearly uniform magnetic field inside, and a toroid, a donut-shaped coil with a magnetic field confined inside. And now, how is the current related to the magnetic field? The current and the magnetic field are related through Ampere's law, which states that an electric current generates a magnetic field around it. The relationship depends on the geometry of the current carrying conductor.